Next part with stoichiometry, we're going to be looking at problems that are called limiting excess reagent problems and also percent yield problems. So we're going to look at limiting excess reagents problems first, and I have two examples for those for you. So the first one says, if 30 grams of benzene reacts with 65 grams of bromine, what amount in grams of bromobenzene would be produced? Okay, so with limiting excess reagent problems, we're going to be given two knowns. The unknown stays the same for both of them, but since with most reactions we have two reactants, and they actually do have amount for each one. So this is a little bit more ideal if you were working in a lab and trying to figure out how much of a product you're supposed to be getting from a reaction. Since you have two reactants, they have their own amounts. We would have to use both of those to calculate out how much of our product would be when we're trying to do this. So setting this up, benzene is C6H6, so that's one of our knowns, and bromine is the other known. Our unknown is going to be, if we go, what amount in grams of bromobenzene? Okay, so bromobenzene, one of our products, we have HBr, that is hydrobromic acid. And if we look at this, benzene was C6H6, bromine Br2, bromobenzene, since it has, benzene has 6 carbons in it and some hydrogens, bromobenzene is going to be C6H5Br. And if we look at balancing, 6 carbons, 2 bromines, 2 bromines, 6 hydrogens, 5 over here, plus 1 more, 6. So it's already balanced. And that's kind of nice for us for this first problem. So let's kind of start with benzene as our first known. And it says that we have 30 grams of it. So we're going to follow that flow chart once again, start with the amount of known, so 30 grams of benzene, C6H6, and we're going to go 2 moles of known, so 1 mole of C6H6 over, and we need to calculate out what is the molar mass of benzene, 6 times 12.01 plus 6 times 1.01. Coming up with a molar mass of 78.12 grams. And grams of benzene get canceled out. The numbers still stay, but the units get canceled out. Now we're going to go to moles of unknown, and we use our mole to mole ratio. Well, in front of our unknown we have coefficient 1, so we have 1 mole of C6H5Br over, and for benzene our known also has coefficient 1. 1 mole C6H6 moles benzene get canceled out. Then our last step is, since we're trying to figure out how many grams, we need to go to mass of the unknown. So in our last ratio, up in the numerator, we're going to have the molar mass of bromobenzene. 6 times 12.01 plus 5 times 1.01 plus mass of bromine is 79.90. I'm coming up with a molar mass of 157.01 grams. C6H5Br over 1 mole C6H5Br. So moles of bromobenzene gets canceled out. So here's our setup. Now let's kind of run this through our calculator and see what our numeric answer comes out to be. I'm going to take 30 times 157.01. That's divided by 78.12. And I'm coming up with 60.30 grams of bromobenzene. Now what we're going to do is we're going to set up another stoichiometry problem, and this time our unknown still stays the same as I said, but our known is going to be bromine. And we're starting off with 65 grams of bromine. And we're going to go to moles of bromine. So 1 mole of Br2 over, and mass of diatomic bromine, 79.90 times 2, 159.80 grams. Okay, now we're going to go to moles of unknown. Mole to mole ratio unknown over known. So 1 mole of bromobenzene over 1 mole of bromine. Moles of bromine get canceled out. Then our last step is to go to grams of bromobenzene, and since we already calculated out up here, we're going to use the same number down here. 157.0201, grams C6H5Br over 1 mole C6H5Br. Okay, let's run this through the calculator. So 65 times 157.01 divided by 159.80. Okay, so we have two possible answers. Which one is going to be the correct one when we're trying to figure out how much of our product we're going to get from a reaction? Well, the answer is going to be we go with the smallest number. So in this case, 60.30 grams of bromobenzene is what we're going to get from this reaction. Okay, now this is telling us that our limiting reagent is benzene, because it limits the amount of the product that we're going to be able to get. Our excess reagent, on the other hand, is going to be bromine, because since it gave us the higher number, this is telling us that we have some bromine left over. It's in excess. So let's look at another example of limiting excess. So in this problem it says, in the reaction below is how electricity is produced in a hydrogen fuel cell. If the fuel cell contains 150 grams of hydrogen and 1500 grams of oxygen, how many grams of water can form? Now this one we're going to find out a little bit more information. What is the limiting reagent? It's kind of like what we did up here with this problem I showed you at the end. We're going to figure out the excess reagent. And then the last part is how much of the excess reagent remains. So in this problem, let's go ahead and let's mark our known and unknown. This one's pretty easy because we only have one product. So that is our unknown. And our two reactants, it's going to be our knowns. Now balancing this, 2 hydrogen, 2 hydrogen, 2 oxygen, 1 oxygen. So to get 2 oxygen over on the right hand side, I'm going to put a coefficient 2 in front of water. That gives us 4 hydrogen on the right hand side, and we need to get 4 hydrogen on the left hand side. So now this is balanced. I'm going to flip the page over so I have the space to work on this, and let's start with our 150 grams of hydrogen as our known. Okay, so just like our flow chart, we're going to go from amount of known to moles of known. 1 mole of H2. Now, mass of diatomic hydrogen, 2 times 1.01, 2.02 grams. Then we're going to go to moles of unknown, so our mole to mole ratio. So if we look at our reaction, we have 2 moles of water over 2 moles of hydrogen. Now, one of the things I haven't shown you yet, look at our mole to mole ratio, 2 over 2. If you can reduce the mole to mole ratio, by all means do so. So 2 over 2 turns into 1 over 1. Then we're trying to figure out how many grams of water we're going to get from the reaction. So the last step is to go to grams of water. That's our amount. So the mass of water, we have 2 hydrogens, 1 oxygen. So 2.02 plus 16, 18.02 grams. H2O over 1 mole H2O. So here's our first setup. Now let's run this through our calculator. 150 times 18.02 divided by 2.02. I'm coming up with 1,338.12 grams water. Now let's have oxygen as our known, and we had 1,500 grams of oxygen. So just like we were doing before, we go to moles of known, so 1 mole of O2 over, now the mass of diatomic oxygen. One oxygen atom is 16 grams, so 2 times 16 is 32 grams. So grams of oxygen get canceled out. Now moles of unknown. Our mole-to-mole ratio this time around, we have coefficient of 2 in front of water, we have a coefficient of 1 in front of oxygen. So our mole-to-mole ratio in this one would be 2 moles H2O over 1 mole O2. Now this one we can't reduce because, you know, it's not 2 over 2 or 4 over 2 or 2 over 4. If you can reduce the numbers in the mole-to-mole ratio, by all means, do so. Make it a little bit easier on yourself. Then the last step, go to mass of the unknown, so 18.02 grams of water over 1 mole water. Moles get canceled out. Alright, so let's run this through our calculator. We're going to take 1,500 times 2 times 18.02 divide by, down there we only have one number. We only have 32. So all three of those numbers times multiply together and then divide by 32. And I'm coming up with 1,689.38 grams H2O. Okay, so looking back at our problem, you know, our first question, how many grams of water can form? Well, looking at our two possible answers, we have 1,338.12 grams of water and 1,689.38 grams of water. We have to go with the smaller answer every time. So, first question, how many grams of water? We're only going to get 1,338.12 grams of water. Next question, what is the limiting reagent and the excess reagent? Okay, so our limiting reagent is the known that gave us a smaller number. So in this situation, our limiting reagent is hydrogen. The excess reagent is oxygen because it is the known that gave us the higher number. Now the last question, how much of the excess remains? How are we going to figure this out? Okay, well the way that we're going to do this is we're going to take the difference between our two answers that we came up with. So let's go ahead and take 1689.38 grams. And we're going to subtract 1338.12 grams from it. Coming up with 351.26 grams. And the way that we're going to figure out how much of our excess remains is we're going to take our stoichiometry formula, we're going to turn around and flip it upside down. So what we are doing is making water our known and oxygen our unknown. Okay, so this is this is our ratio that we ended up with. So we're going to start with it, but flipped upside down. We're going to go to moles of water. So 1 mole of H2O over 18.02 grams H2O. So grams of water get canceled out. Next step is go to moles of unknown. Well, up here our mole-to-mole ratio was 2 to 1. We're going to flip it. 1 mole O2 over 2 moles H2O. Moles of H2O get canceled out. Then our last step is go to grams of unknown, which we're going to go to grams of oxygen. So we're going to take this and flip it upside down over here. 32 grams of O2 over 1 mole O2. So 351.26 times 32, that's going to be divided by, I'm going to take 18.02 times 2. And I'm coming up with 311.88 grams O2 remaining. Okay, so from the 1500 that we start off with, we have 311.88 remaining. Now, why would we need to figure out how much of the excess remains? Chemicals cost money. So companies, if you're working as a chemist, companies want the chemist to begin using up all the reactants, not having anything left over. Because let's say this is $311.88. So every time that you're in this reaction and you start off with these two amounts, you would be wasting $311.88. And if you run this reaction 5 days a week, 52 weeks in a year, cost starts to increase drastically. So the company would tell you, okay, so you need to cut back on the oxygen so that you're using up both the hydrogen and the oxygen and nothing is left over. That's why we would need to figure out how much of the excess remains. Now, the second part of this video deals with what's called percent yield, because when we're running a reaction, Murphy's Law takes place. If you don't know what Murphy's Law is, it means that anything that can happen will happen, or as one of my professors would say, doo-doo happens. So we calculate out what is the percent yield of the reaction. And let's kind of look at two examples there. So our first one says determine the percent yield if 13.1 grams of calcium oxide was collected when 24.8 grams of calcium carbonate decomposes. Alright, so from this problem we still need to figure out what our known and unknown are. And if we look at this first part, it says determine the percent yield if 13.1 grams of calcium oxide was collected. This is telling us that the reaction took place and that's how much calcium oxide they got from the reaction. The calcium oxide is our unknown. And then it says when 24.8 grams of calcium carbonate decomposes, so calcium carbonate is our known. Now, what stoichiometry shows us, it shows us what we should be getting from a reaction. Okay, in theory, this calculated number is what we should be getting from the reaction. Okay, so what we're going to do is we're going to set up a stoichiometry formula, figure out how many grams of calcium oxide we should be getting from this reaction. So we're going to start with our known, 24.8 grams of calcium carbonate, CaCO3. Then, just like what we've been doing before, go to moles of known, so 1 mole of calcium carbonate over, and I'm kind of drawing a blank on calcium's mass. Sorry, so calcium 40.08 grams plus 12.01 plus 3 times 16. Coming up with a mass of 100.09 grams for calcium carbonate. Grams gets canceled out. Now, we need to go to moles of known. Now, we didn't really look at our reaction to balance it. 1 calcium, 1 calcium, 1 carbon, 1 carbon, 3 oxygen, 3 oxygen. So we're good to go there. Everything's on a 1-to-1 ratio. So mole-to-mole ratio, moles of unknown over known, so 1 mole of calcium oxide over 1 mole calcium carbonate. So moles of calcium carbonate get canceled out. Now our last step is we need to go to the amount of our unknown. Now since we are dealing with grams, that's telling us that with our stoichiometry formula we should figure out how many grams of the unknown we have. So the formula mass of calcium oxide, 40.08 for calcium, oxygen 16, 56.08 grams over 1 mole. Alright, so Now if we take 24.8 times 56.08, that's all divided by 100.09, come up with 13.90 grams. Okay, so this is our theoretical yield. In theory, that's how much we should be getting. This number up here, this 13.1 grams that was collected, this is the actual yield, because when they ran the reaction, that's what they actually got. So to find our percent yield, we take the actual yield, divide by the theoretical yield, and we multiply by 100. Or this problem, actual yield 13.1 grams, divide by theoretical 13.90 grams times 100. 13.1 divided by 13.90 times 100, and we're coming up with a percent yield of 94.24%. Is that a good percent yield? Well, it kind of depends on where you're working at. If you're working for a chemical company, this is not a good percent yield. They want percent yields at least 98%. They want either 99% or 100%, because if you're getting 100% yield, what you're putting into it, that's what you're getting out of it. You're not wasting anything. Academia, if you got 94.24% on a reaction that you're researching, that's wonderful. A lot of times in academia, the percent yield would be down in the 50s or 60s. All right, let's look at one more example of percent yield for today. And I will be doing subsequent videos over limiting reagent and percent yields to help you out a little bit more. But to close out this video for today, let's look at one more example. If 50 grams of silicon dioxide is heated with an excess of carbon, 27.90 grams of silicon carbide is produced. What is the percent yield? Okay, so if 50 grams of silicon dioxide is heated with an excess carbon, and that was produced. So the 50 grams of silicon dioxide, that is our known for our stoichiometry problem. Silicon carbide, since it was produced, that's telling us that they were in reaction, that's what they got. So silicon carbide is our unknown. Let's figure out what our theoretical yield should be for this problem. But before we do that, let's kind of look at our reaction, see if it's balancing on it. One silicone, one carbon, good to go there. 2 oxygen, 1 oxygen. So we need to put a coefficient of 2 right there to balance out the oxygens, but that gives us 2 carbons on the right-hand side. So we need to have 2 carbons on the left-hand side. Now it's balanced. So figuring out theoretical yields, start with 50 grams of silicon dioxide. We're going to go to moles of silicon dioxide. Now the mass of silicon dioxide, we have 28.09 plus 32, so 60.09 grams, SiO2. So grams of silicon dioxide get canceled out. Now we're going to go to moles of unknown. Now our mole-to-mole ratio, our unknown over known, kind of nice, it's a 1-to-1 mole ratio. So 1 mole SiC over 1 mole of SiO2. Silicon dioxide gets canceled out. Then, since we are dealing with grams up top, we're going to figure out how many grams of silicon carbide we should have got from this reaction. So we need to figure out what is the molar mass of silicon carbide. 28.09 plus 12.01. I'm coming up with a mass of 40.10 grams. That'll be over 1 mole SiC. So there's our setup. 50 times 40.10 divided by 60.09. I'm coming up with 33.37 grams. Okay, and once again, this is our theoretical yield. Up here, the 27.9 that was produced, this is the actual yield. So percent yield, actual yield over theoretical yield. And since it's percent, we have to multiply 100. I can't remember if I put that on the back on the other one. Yes, I did. But yeah, since it's percent, we have to multiply by 100. So our actual yield, 27.990 grams, over our theoretical yield, 33.37 grams, times 100. Coming up with 83.61% for this one. Okay, if you have any questions about this stuff, please email me, and I will talk to you later. Thank you.